In this problem, we're going to deal with the electric potential due to a point charge rather than a uniform electric field. So I've already drawn the picture. We have two charges, a positive and a negative charge, Q1 and Q2, and then we just have a point in space at point A. Currently there is no charge there, and we want to find the electric potential at that location A. So to do that, just recognizing that the net electric potential, or the net voltage, at point A is equal to the potential created by charge 1 at point A and the potential by Q2, again at point A. To calculate those two individual potentials, we have the point charge equation for electric potential. So that's K Q1 over R1 for the distance. So that R1 is going to be the distance from the location of Q1 to the location of A. And then we add that to the other one, K times Q2, and that's over R2, which is the distance from Q2 to location A. Plugging in numbers, 8.99 times 10 to the 9 Newton meter squared per Coulomb squared. And the charge 1 is 8 times 10 to the minus 6 coulombs. And the distance is not exactly shown. We have a triangle. I'll just go ahead and dash in the distances here. So there's the 4 centimeters, there's the 3 centimeters, and this is the distance R1. So that is a 3, 4, 5 triangle, so that is 5 centimeters or 0.05 meters. And we add that to the other one, 8.99 times 10 to the 9 Newton meters squared divided by Coulomb squared. And Q2 is a negative, and you have to include the negative, 10 to the minus 6 coulombs. And then that distance is 3 centimeters or 0.03 meters. And so adding up all of that is 8.39 times 10 to the 5 volts. And that's what we were asked. And I'm just going to highlight that you need to make sure you include the negative on a charge when it's there, because I had to ultimately subtract the two potentials because one of the charges was negative. And notice that there was no vector math. This was scalar math. So I just had to add, or in this case, subtract the numbers without worrying about angles. So now let's do part B. And in part B, we're going to add or bring in a third charge, which is 2 microcoulombs, to location A. And the question is, what is the electric potential energy of Q3? All right, so to get that answer, I'm just going to use the electric potential energy equation. It's equal to the object charge, in this case Q3, times the electric potential at that point. So this is the net electric potential at point A, which is what we calculated in part A. So the charge is 2 times 10 to the minus 6 coulombs, and the electric potential is 8.39 times 10 to the 5 volts. So that comes out to be 1.68 joules. Joules because potential is energy. Okay, and now part C, I'm going to flip the page for that one. So part C, what is the electric potential energy of this 3-charge arrangement? And the semantics here are important. The 3-charge arrangement. So what I'm asking for is the electric potential energy of that whole system of 3 charges. The way to get to the answer, the technique for doing this, is to bring each charge in one at a time and calculate the potential energy once that charge is in place. So we'll start with charge 1. Start with Q1 and alone. So what I mean is there's nothing there yet. I now come over and bring in charge 1. So maybe down here at the bottom, I'll just go ahead and show that we're now putting charge 1 in place. And there's nothing else there. Let's go ahead and put the value on it. Now there's no other charge in the area, so there is no electric potential where I had just put charge 1. So this is an easy one. The potential energy associated with bringing in charge 1 is 0. And that is because it is alone. And you just can't have potential energy associated with just one object. It's actually a rule in physics. You may have heard that rule in mechanics or not. But if you just have one object, there's no potential energy. You need two so that they are acting on each other. They have a force on each other. Okay, so now we bring in the next charge. So I'm going to calculate the electric potential by Q1 at location of Q2. So just thinking about the location of Q2, let's go ahead and get the potential there before I actually, I guess, put the charge there. So that's KE Q1 over R, and that's the distance between 1 and 2. Let me go down to the picture and show what I'm doing. So now I have this location. I'm going to put Q2 there, but right now it's just a location. And here's the distance. Okay, so plugging in numbers for that. 8.99 times 10 to the 9. The charge, 8 times 10 to the minus 6. And the distance from Q1 to that location, 0.04 meters. So that comes out to be 1.80 times 10 to the 6 volts. Okay, so that's the potential. Now to get the potential energy of Q2, now that we have put it in that spot, and let's go ahead and do that in the picture. So now we're putting Q2 here. So that is simply Q2 times the potential at that location. It was the potential by Q1 that we just calculated. So that is minus 2 times 10 to the minus 6 for Q2. And the potential at that point, 1.80 times 10 to the 6 volts. So the potential energy then of Q2 is negative 3.60 joules. So we have that value, and we have the value by Q1, which was 0. So now let's bring in the third charge. We sort of repeat that process we did for charge 2. I first look at the position where it's going to be, so I'll show that position down in my picture. And we figure out what the voltage is there first. Then we bring in the charge, and that's going to be the positive charge. Q3 is 2 microcoulombs. And we do the calculation for all of that, and that is exactly what we did in part B. So let's just not redo that. So from B, we have already found the potential energy, Q3, is 1.68 joules. So now we have all of the potential energies. Now we can get the net potential energy of the system. Potential energy net of the 3-charge system, and that's equal to, we have a minus 3.6 joules, and we have a positive 1.68 joules, and that comes out to be minus 1.92 joules. So now on a new page, we'll do part D. We're going to start with the 3-charge arrangement again. All 3 of those charges are just like before. And then if we allow Q3 to be pushed away from the other ones, we release it, we'll hold Q1 and Q2 in place. And then when Q3 gets really far away and it reaches its final velocity, and it just keeps going at that velocity, that speed, then what is that speed when it gets really far away? So that's what we want to calculate. To do this, we do need to know what the mass of Q3 is, so we have been given that information as well. So now to get this, we're going to do an energy analysis of Q3. And it makes sense to do that, I think, because we have an initial potential energy for it, we have a final potential energy for it, and we want to get the final speed, which is associated with the final kinetic energy. So I think from that respect, you can decide that the conservation of energy is a logical place to start. So that's the change in the kinetic energy plus the change in the potential energy is equal to work done by any other forces. Okay, well, let's look at the work first. Are there any other forces other than the electric force? And the answer is no. There's only the electric force, and the electric force is already included in the potential energy term, so I don't have any other forces to deal with, so I don't have work by any other forces. So now we have the final kinetic energy minus the initial kinetic energy, and we have the same with the potential. We have the final potential energy minus the initial potential energy. So let's think about the kinetic energy. It starts at rest and then it gets really far away and it's moving at some speed. So it has a final kinetic energy, but it does not have an initial because initially the speed is 0. So let's find the potential energies to put in here for the initial and the final. Let's think about the initial picture. The initial potential energy is the amount of potential energy that Q3 has when it is in the configuration that I've just drawn above. Well, that's what we figured out in Part B again. We used that value a couple of times, and now we're using it again. So from Part B, it's 1.68 joules. So that was the potential energy for Q3 from Part B. Now let's look at the final. So we have the final potential energy. Now this is the final potential energy, not of the system. We're doing all of this analysis about Q3. So we want the final kinetic energy of Q3. So that's going to be Q3 times the potential. So what would that be? Well, we know what Q3 is, but we need to get the net at this final location. So in the final location, I'm going to go ahead and just write out the whole equation so we can see exactly what happens. So we have the final distance. So this is the potential associated with Q1, and then we have also the potential associated with Q2. So these are the final distances. So this is the distance from Q1 to the final location, the distance from Q2 to the final location. But what are those distances? In the statement, it says, what's the speed when it's very far away? Let me underline that term right there, very far away. And we can interpret that to mean that r essentially might as well be infinity. It's extremely far away. And that's what we're putting in here. Both of these r's here, whether it's to Q1 or it's to Q2, are infinity. So I'm dividing by infinity. That makes the term 0. So both of these are 0. So the net potential is 0. And so I can see that the potential energy, the final potential energy, is 0. It doesn't have any when it gets really far away. So now what are we left with in our energy equation? Back all the way up, and we have kinetic energy, which is 1/2 mv squared, mv initial squared, minus the change in the potential energy, but we only have the initial. So that's negative 1.68 joules. That equals 0. So we were given the mass, 5 times 10 to the minus 10 kilograms. I wrote initial speed, but this is the final speed that goes there. There was no initial speed. So now we've solved for the final speed, and that is 8.20 times 10 to the 4 meters per second. And that's the end of this problem.